today is day 2 of section 7.3. Section 7.3 is a sampling distribution for sample means. This is a pretty big deal in terms of stuff that we're going to be using for the rest of the course. Decent amount of material was thrown at you in the last lesson. This will recap the highlights in terms of facts and formulas, and then a few more practice problems that address this. And so when we choose many simple random samples from a population, the sampling distribution of the sample mean is centered at the population mean mu and is less spread out than the population distribution. Okay, specifically, here are the facts. Suppose that x bar, which is sample mean, is the mean of an SRS of size little n, drawn from a large population with mean mu and standard deviation sigma. Then, the mean of the sampling distribution, which is the mu sub x bar, is equal to the population mean. The standard deviation of the sampling distribution of x bar, this is the symbol for that, standard deviation sub x bar, means the standard deviation of the sampling distribution, population standard deviation divided by the square root of sample size. Okay, that formula is only valid as long as we are not sampling more than 10% of the total population. Okay, these facts about mean and standard deviation are true no matter what shape the population distribution has. So whether we know it's approximately normal or know it's distinctly not normal, these particular facts have no bearing on population distribution. All right, well, what if we do know population distribution? Okay, if the population distribution is normal, and so is the sampling distribution, no matter what the sample size is. If the population distribution is not normal, the central limit theorem tells us that the sampling distribution of x bar will be approximately normal in most cases if n is greater than or equal to 30. Okay, we're going to consider all cases, and it's always going to be the 30 as the magic cutoff. Sometimes it doesn't have to be 30, but we're going to use as the universal rule, regardless of population distribution shape, as long as we have a sample size of at least 30, we're going to assume approximately normal for the sampling distribution. Okay, this is critical because the central limit theorem, or CLT, you can use that abbreviation, allows us to use normal probability calculations to answer questions about sample means for many observations, even when the population distribution is not normal. All right, so these are some problems from the textbook for the first few here that were not part of the classwork or homework we've done so far. So number 53 from page 462. Suppose that the blood cholesterol level of all men aged 20 to 34 follows a normal distribution with mean of 188 milligrams per deciliter and a standard deviation of 41 milligrams per deciliter. Okay, choose a simple random sample of 100 men from this population. Describe the sampling distribution of x bar. Okay, well, describing the sampling distribution, you want to discuss what is its shape, what is its mean, what is its standard deviation. Those are the things that would be looked for by AP rubric. Well, if we know that the population distribution is normal, no matter what the sample size is, the sampling distribution will also be approximately normal. Even if we didn't know that, with a sample size of at least 30, the population distribution will be approximately normal. So we can justify that normality either one of those two ways. As far as the mean goes, the mean of the sampling distribution is the mean of the population, which is the 188 milligrams per deciliter. As long as we're not sampling more than 10% of the total population, this standard deviation formula kicks in. Population standard deviation divided by the square root of the sample size. And for this, we would want to make sure that we have the units as well. Okay, B, find a probability that x bar estimates mu within plus or minus 3 milligrams per deciliter. Well, within 3 milligrams per deciliter of the mean would be the 188 minus 3, 188 plus 3. So we know that our sampling distribution is approximately normal. So we can use the normal CDF. We've just identified the upper and lower bounds, the mean and standard deviation. We've just calculated from the previous problem. So that command gives us our probability for that particular question. Okay, part C. Choose a simple random sample of 1,000 men from this population. Now what is the probability that X bar falls within plus or minus 3? So everything is the same except for that 1,000 is replacing 100. So it's going to make the standard deviation of the population distribution smaller. So that changes the last number in our normal CDF command, and we get almost 98%. Show your work. Well, that's obvious for this. In what sense is a large sample better? The larger sample is better because it is more likely to produce a sample mean within 3 milligrams per deciliter of the population mean. So that larger sample size gives us less variability, more likely to hit that plus or minus 3 mark that they're looking for this. Okay, next one is from page 462 in your textbook, number 55. A bottling company uses a filling machine to fill plastic bottles with cola. The bottles are supposed to contain 300 milliliters, but in fact the contents vary according to normal distribution with a mean of 298 and a standard deviation of 3. Okay, what is the probability that a randomly selected bottle contains less than 295? Show your work. All right, it says specifically in the problem that we have a normal distribution. So if we have a normal distribution, we can answer questions based on sample sizes of less than 30, specifically just one bottle here. So less than 295, lower bound, arbitrarily very small number, or very negative number. Upper bound, mean standard deviation, looking at a little bit less than a 16% chance. Okay, what is the probability that the mean contents of 6 randomly selected bottles are less than 295? So instead of one bottle being less than 295, what's the probability that the average of 6 bottles is less than 295? So as long as 6 bottles is less than 10% of all bottles produced, we can use this formula. So that's the standard deviation. I recommend you actually put this in as is, rather than a decimal approximation of that. Keeps it a little bit more accurate. Most situations, it's probably not going to matter, but it could. It's safer to use that than this. So that brings the probability down to less than 1%, 0.0077 tenths of 1%. All right, next one from the textbook. In response to the increasing weight of airline passengers, Americans are basically getting fat, the Federal Aviation Administration told airlines to assume that passengers average 190 pounds in the summer, including clothes and carry-on baggage. But passengers vary, and the FAA did not specify a standard deviation. A reasonable standard deviation is 35 pounds. Weights are not normally distributed, especially when the population includes both men and women, but they're not very non-normal. A commuter plane carries 30 passengers. They explain why you cannot calculate the probability of a randomly selected passenger weighs more than 200 pounds, and we do not know the shape of the distribution. If it is distinctly not normally distributed, and we're only talking about one passenger, we can't use normal CDF. Now, maybe there exists some formula for whatever the shape of the population distribution is, but we're not aware of it. As the information is given, we can't solve that. Find the probability that the total weight of 30 randomly selected passengers exceeds 6,000 pounds. Show your work. Well, if we're talking about 30, a sample size of 30, now the sampling distribution is approximately normal. So we need to rethink this a little bit. Rather than thinking about the total of being 6,000, what we want to think about it is if 30 have a total of 6,000, then we're talking about an average of 200 pounds for that group. So this question can be thought of as finding the probability that the average weight of the 30 passengers does not exceed 200 pounds. So 30 is less than 10% of all airline passengers, so our standard deviation formula is allowed. Our sample size is at least 30, so we know the sampling distribution is approximately normal. That allows us to use the normal CDF with the numbers above, so you're looking at a little bit less than a 6% chance that the mean weight exceeds 200 pounds. All right, this is an AP question from a previous test. There's not really anything new in content here, just looking at a way you can approach this in multiple choice format. The tires sold at Best Tires last an average of 80,000 miles with a standard deviation of 12,000 miles. Assume that the wear of tires is approximately normally distributed and the wear of each tire is independent. Which of the following describes the sampling distribution of the mean number of miles that a set of 4 randomly selected tires purchased from Best Buy Tires will last? Well, the first thing here is approximately normal, approximately normal, approximately normal, approximately normal. The shape of the sampling distribution is unknown. Okay, so that's the first thing I'm going to focus on. Okay, the population standard deviation is approximately normally distributed. So regardless of sample size, the sampling distribution is going to be approximately normally distributed. So we can know for sure the shape. So that eliminates, it can't be E. It's going to be one of these 3 or one of those 4 guys right there. One thing that is a very common variation with these types of questions is one of those guys saying exactly normal or having normal without the approximately, in which case you can eliminate that, but in this case we cannot. All right, next thing I'm going to focus on. The mean of the sampling distribution is equal to population mean, which is 80,000. So that eliminates this one right here, the mean of 320,000. That's no good. These are all mean of 80,000, mean of 80,000, mean of 80,000. So now it comes down to we need to break the tie with standard deviation. We have standard deviations of 3,000, 6,000, and 12,000. All right, there's an answer for all of these at this point, so it's not like we have to concern ourselves with the 10% check or anything like that. We know that one of these exists. Okay, the formula is population standard deviation divided by the square root of n. So the population standard deviation is 12,000. Our sample size is 4. The square root of 4 is 2. So 12,000 divided by 2 gets us to C as the final answer. All right, this is a multiple choice from your textbook. The number of hours a light bulb burns before failing varies from bulb to bulb. The population distribution of burnout times is strongly skewed to the right. Okay, so that's probably going to be pretty important. The central limit theorem says, as we look at more and more bulbs, the average burnout time gets closer to the mean U for all bulbs of this type. All right, that is relatively true, but is it a direct result of the central limit theorem? So this is a possibility. That's not bad, but maybe we could do better. Okay, the average burnout of a large number of bulbs has a sampling distribution with the same shape strongly skewed as the population distribution. Well, large number in the context of this little corner of our stat world, that would refer to sample size greater than 30. That would be considered a large sample size. And with a large sample size, the sampling distribution becomes approximately normal. It's not going to have the shape that's going to be similar to the population distribution. A small sample size would have a similar shape, but not a large sample size. We can confidently eliminate D. The average burnout time of a large number of bulbs has a sampling distribution with a similar shape, but not as extreme, skewed but not as strongly as the population distribution. Okay, this is a very similar response to C in terms of a large number. A large number in this context means at least 30. So we're looking at approximately normal, not resembling the population distribution. So we can pretty confidently eliminate C. The average burnout time of a large number of bulbs has a sampling distribution that is close to normal. Okay, that seems to be a pretty good one. The average burnout time of a large number of bulbs has a sampling distribution that is close to normal. Okay, that's a contender. Let's come back to that one and see if there's something better. The average burnout time of a large number of bulbs has a sampling distribution that's exactly normal. There's never anything that's exactly normal. So that one we can confidently eliminate. So as this is kind of true, leaning in the right direction, this is more right on target in terms of the central limit theorem. This is a direct product of the central limit theorem. So we're going to break the tie with A and D with the D. All right, this is another question that was an actual AP question that I think is pretty tricky, a little bit more challenging than the ones we've done so far. A simulation was conducted using 10 fair 6-sided dice, where the faces were numbered 1 through 6, respectively. All 10 dice were rolled. The average of the 10 numbers appearing face up was recorded. This process was repeated 20 times. Which of the following best describes the distribution being simulated? All right, well, one thing that's misleading in the beginning, in terms of potentially misleading, is what is the deal with that 20? Okay, the 20 is the simulation of the sampling distribution. The sampling distribution will be all possible things that could occur. Can't do all possible, but we're going to simulate it with 20. The actual sample size is the 10. It's the sample size of 10 that's being repeated many, many times. So let's take a look and see, based on just that, what are we looking at here? A sampling distribution of sample size, a sampling distribution of a sample mean with n is equal to 10. Well, so far that statement is on target. A sampling distribution with a sample mean of 10, n is equal to 10. That's on target. A sampling distribution of a sample mean with n is equal to 20. No, the 20 is the number that's used to approximate the sampling distribution. We can eliminate that because this is false. A sampling distribution of a sample proportion. Well, we're talking about means here. The average number of the 10 numbers. We're not talking about proportions. So that can be eliminated. That can be eliminated. All right, so now we're down to, well, what's the deal with breaking a tie? The mean of the sampling distribution being 3.5, well, that's the same for both. So now it comes down to the standard deviation of the sampling distribution. So for this one here, what I'm going to do is turn to my calculator. I'm going to go to Stat, Edit, and I'm going to create the probability distribution here. The possibilities are the faces could be 1 through 6, and the probability of each is 1/6. So the distribution for rolling one die would be this right here. I'm going to run one variable statistics for this distribution. And the very first thing is the mean of 3.5. And for one dice or one die, the standard deviation is 1.707. We're looking at a group of 10. So for a group of 10 or a sample size of 10, we'd have to divide by it by the square root of 10. So 1.707 divided by 10, root 10 rather, that's that 0.54. So that breaks the tie between A and B. B would be the correct answer if we were only rolling one die, a group of 10, it would be the, A would be the correct answer. I might have said that backwards. We're eliminating B because that would be if we were rolling one die for the group of 10, we would need that.